Okay, so with Archimedes' principle, we're revisiting an idea that we covered in Physics 1, and that was Newton's third law. For every action, there's an equal and opposite reaction. Now, Archimedes lived long before Newton, so this idea is probably the first idea related to the law of interactions. Obviously, Archimedes only applied it for fluids, but we can think about it as, again, you put a force on an object, that object will put a force back onto the object, which is exerting the original force. Now, Archimedes lived 287 to 212 BC, so again, long before Newton. He was a Greek mathematician, physicist, and engineer. And this principle of buoyant forces simply stated that when you displace a fluid, okay, can be partially submerged or fully submerged, the force of buoyancy, the upward force pushing the object back up, is going to be equal to the weight of the fluid displaced. Okay, so again, we think about this object as displacing a fluid. Okay, here we have, let's say, a bowling ball or something, and a bowling ball is more dense than water, so it's going to sink, but still it's going to experience a buoyant force. Okay, so it displaces its weight in water equal to what weight would be displaced by that volume, and that's equal to the buoyant force. So objects that are more dense than water, they're going to sink because they don't displace enough fluid or enough weight of fluid. Objects that are lighter than water or less dense than water will float and only be partially submerged. But again, think of Newton's third law. For every action, there's an equal and opposite reaction. The object pushes the water out of the way. What does the water do? It pushes back on the object. Oops. Okay, next slide. So again, the physical cause of the buoyant force can be seen. Remember, pressure increases as a function of depth. So if we look at it right here, we can clearly see that on the bottom of the bowling ball, there's a larger force. Okay, there's a greater force pushing on it because the weight of the fluid is greater at that depth than the weight of the fluid at the very top. So this unequal pressure, where you have a lower pressure on top, I don't draw very well, but we'll do that. I'll just do higher pressure on the bottom. I'll use an H, okay? That results in a net force, and that net force, again, is our buoyancy, okay? So, simple idea, nothing really complicated right here. Again, can be thought of as Newton's third law, but could also be thought of as a difference in pressure where the pressure is greater underneath the object and lower at the top of the object. So again, weight pulls the object down, the buoyant force pulls the object up. And the fluid weight that we displace is simply going to be equal to the buoyant force weight. So again, think about swimming, think about being immersed in the water. Humans are close to being neutrally buoyant. I mean, we all have different densities depending on our body type. But for the most part, when you swim, you don't have to exert very much force to stay above the water, okay? And that's really due to the fact that you're displacing a certain amount of fluid weight. Hot air balloons, again, gases, liquids, even a plasma is considered to be a fluid. So we can apply Archimedes' principle to hot air balloons. Now, how does a hot air balloon, which of course contains air, actually float? Well, the principle, again, isn't all that complicated when we think about it. When you heat air, it tends to expand. So basically, you've got this big envelope of hot air in this nylon envelope. No, that's redundant. But in any case, um, we're going to displace the cold air, which is more dense and has more weight. The problem that we have here is, first of all, air doesn't have a tremendous amount of density. Okay, it doesn't have a tremendous amount of mass per volume. So you need a tremendously large mass, or I should say tremendously large volume to get that difference in weight between the hot air and the cold air. So again, thinking about how a hot air balloon is able to float in the air, it's the difference between the weight of the hot air in the envelope and the cold air, which it's displacing, that gives you your buoyant force. All right, let's go to an actual calculation. It's a little bit complicated, so bear with me as I go through the different calculations. So this equation represents the weight of the cold air that we're going to displace. We have a total volume of 2,800 cubic meters. That's a tremendous amount of volume. But remember, unlike water, which is about 1,000 kilograms per cubic meter, the mass of air is closer to about 1 kilogram per cubic meter. So it's 1,000 times less dense. We're going to need 1,000 times more volume to get the same weight difference. So cold air, we can take the density of cold air, 1.225 times 10 to the, 1.225 kilograms per meter cube, multiplied by the volume and multiplied by the acceleration of gravity. Remember, we're doing weight here, so you've got to multiply by the acceleration of gravity. So looking at this, the weight of the cold air, which is being displaced, is 33,600 newtons. All right, so we're replacing cold air with hot air, but the hot air does have mass to it, okay? It has mass, so it has weight. Notice the density is much lower for the hot air in the balloon, okay? We're increasing the temperature to around 100 degrees Celsius, which is about all this nylon can really take. You get much higher than that, and the nylon envelope becomes damaged. So looking at that hot air, we have 26,000 newtons. So once again, this is going to be the weight of the fluid which is being displaced, and this is going to be the weight of the fluid which we're replacing the cold air with, okay? So as we can see here, that difference, what now becomes the buoyant force, okay? Well, actually, the buoyant force is 33,600 newtons. We subtract off the weight of the fluid that we displace, we get a net force of 7,600 newtons. So that shows how the hot air balloon flies, and that shows you why the hot air balloon has to be so large in volume. And again, you think about this, the mass of the hot air balloon includes not only the volume of hot gas, which is in the nylon envelope, you also could put 5 passengers and other equipment. So if we subtract off the difference between the buoyant force and the weight, we get about 725 kilograms is what we can lift, or about a weight of 7,100 newtons. Another use of Archimedes principle is testing antifreeze. Ethylene glycol or propylene glycol are common antifreezes used in car radiators. By the way, ethylene glycol is very toxic. A small amount of it will destroy your liver, so it should be kept away from pets and certainly handled with great care. Propylene glycol is a much safer alternative. So sometimes you'll see these green antifreeze mixtures. But ethylene glycol and water is often used to keep your radiator in the car from freezing. And basically, because ethylene glycol is 11% denser than water, we can use these balls, which are calibrated for different densities. Oops, switch things. And the more balls that float, the denser the fluid. So in the beginning of the winter, when you want to see the quality of your antifreeze, you can actually see, do you have enough protection, or do you need to add more ethylene glycol? Again, in the radiator, you don't use 100% ethylene glycol. It's not a very efficient fluid to transfer heat from the engine, but you don't want to have so little that in very, very cold weather, the antifreeze is going to freeze. Okay, so Archimedes principle, again, if we have a totally submerged object, we can see that the buoyant force is going to be equal to the density of the fluid times acceleration of gravity times the volume of the object. This subscript is in the wrong place. Of course, the downward force is going to be equal to the weight. So the net force, whenever we look at a completely submerged object, is going to be the difference in the density times the acceleration of gravity times the volume of the object. So quite honestly, if the fluid is denser than the object, it's going to float toward the surface. The buoyant force will exceed the weight. If the fluid and the object are the same density, we call this neutral buoyancy, the object will stay submerged, but barely, okay? And obviously, if the object is denser, it's going to sink because the weight is going to be greater than the buoyant force itself. If we're talking about a partially submerged object, then typically the ratio of densities between the object and the fluid will determine how much it floats above the water. Here's just a quick experiment where the Archimedes actually came up with this. We can measure the density of an object by submerging it. What you do is you weigh it, first of all, get the dry weight, okay? And then you compare the dry weight to the weight when it's submerged. Again, going back here, the buoyant force is going to be equal to, the buoyant force minus the weight is going to be equal to the difference in the fluid density minus the object's density times acceleration times the volume. As the legend has it, Archimedes was asked by the king to determine whether his crown was made out of 100% gold. King had suspected that the goldsmith whom he had given the gold to make the crown had substituted other metals in there, such as silver, kept some of the gold for himself. And Archimedes was able to use his principle of buoyancy to demonstrate that, yes, in fact, the crown was not made out of 100% gold. And of course, the goldsmith was executed as a result. This, of course, is a legend. We don't know how true it is. So in this case, we measure the gold crown. Let's say, this is a really tiny crown because gold's dense. Let's say its dry weight is 7.84 newtons. When immersed in the water, it weighs 6.86 newtons. The buoyant force, of course, is 0.98. So you can look at the dry weight, okay, compare that to the buoyant force and determine the density from that. And again, in this particular example, we see that the density is 8 times 10 to the 3 kilograms per meters cubed. Obviously, this is much lower in density than gold, and indicating that the crown is not 100% gold. Okay, the density of the crown at 8 times 10 to the 3 kilograms meters cubed compared to the density of gold at 12.5. Again, obviously something was substituted in here. So there is an application of Archimedes' principle. All right, let's skip ahead a little bit. For floating objects, obviously the objects are at equilibrium. We remember that equilibrium means that the total forces are zero. If something is sinking, it's not at equilibrium, it's sinking, okay? There the weight's greater than the buoyant force. But according to Archimedes' principle, if an object is floating, the weight of the fluid displaced is going to be equal to the weight of the ship. So you can actually measure the weight of a ship by seeing how deep it sits in the water. Again, looking at this, the density of the object divided by the density of fluid will determine what fraction of the object is above the water and what object, fraction is below the water. So again, like this piece of wood, if you're about 50% the density of water, it's going to be half submerged and half below. A little denser, let's say instead of pine, which is about the density of specific gravity of 0.5, let's say you're talking about oak. Oak will be about 80% below the surface of the water and 20% above. So again, looking at an empty ship, you can tell that it's empty without even looking at it because its hull will sit very high in the water. The more cargo you put in the ship, the further it's going to sink. Icebergs are a great example of this. We look at icebergs. The term, the tip of the iceberg. Well, ice is about 90% the density of seawater. This means that only about 10% of an iceberg's volume will be above the waterline. That's why these things are so treacherous, because most of what you see of an iceberg, 90% of it is below the water.